The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, today we resume our theme of memory hierarchy efficient data structures. And last time we saw cache oblivious B trees, which achieve log base B of n for all operations. Insert, delete, search. And the cool part is that we could do that without knowing what B was. And it was basically binary search tree stored in a funny order, this Van M. de Boas order, with an ordered file on the bottom, which we left as a black box. And today we're going to see how to actually do ordered files in log squared n data moves per insert and delete. And then as a little diversion, we'll see a closely related problem to this is called list labeling, which we needed in lecture 1 and left it as a black box for full persistence. We had this version tree with full persistence, and we needed to linearize that version tree into a bunch of numbers so that we could then compare whether one version was an ancestor of another. And for that, we needed to be able to store a linked list and insert and delete in the linked list and be able to query who is this node in the linked list precede this node in the linked list in constant time per operation. So we'll also do that today because it's time. And then we're going to do a completely different cache oblivious data structure that's interesting mainly in the way that it adapts to M, not just B. So remember, B was the size of a memory block. When we fetch something from memory, we get the entire block of size B. M was the size of the cache. And so there were M over B blocks in the cache of size B. So that's what we'll do today. I'm also going to need a claim, which won't prove here, that you can sort cache obliviously in n over b log base m over b of n over b. So I'm going to use this as a black box today. And we're not going to fill it in because it's not a data structure, and it's a data structures class. To give you some feeling for why this is the right bound for sorting, if you know m and b, then the answer is m over b way merge sort. So you all know binary merge sort, where you split into two parts. If you split into m over b parts and then do an m over b way merge, that's exactly what a cache can handle. It can read one block from each of the lists that it's trying to merge. It has just enough cache blocks for that. And then you do the merge block by block, load new blocks as necessary. That will give you a linear time merge, and so you'll get n over b times log base m over b, and it turns out the right thing in here is n over b, or n is basically the same because it's inside the log. It's not a big deal. Okay, so external memory-wise, that's how you do it. You can do this cache obliviously in a similar way to, roughly speaking, in a similar way to the way we do B trees, where you're binary searching on the ways, in the number of ways you should divide your array into. I'm not going to get into details in that. We'll focus on cache oblivious priority queues, which do a similar kind of thing, but get it dynamic. All right, but before we go there, let's do ordered file maintenance. So let me first remind you of the problem. We want to store n items in a file, which think of as an array of size order n. This constant's bigger than 1 with constant size gaps. And then I should say in specified order. subject to inserting and deleting items in that order. So this was the picture. We have an array. We get to store some objects in the array. We can have these blank cells in between, but each of these gaps has constant size. Maybe these data items are sorted, maybe not. And then we're able to say things like, okay, insert a new item 8 right after 7. And so then you'd like to do that. Then you'd also then like to say, okay, now insert new item 9 here. And then this guy maybe gets shifted over. So 12 is over here. This becomes blank, and then you can fit the 9, and so on. You want to be able to do insertions and deletions like that quickly. And quickly here means we're going, whenever we do an insert or delete, we're going to rearrange items in an interval. And that interval is going to be small. Log squared n amortized. That's all I need to say here. I guess we also want to say that when we're moving these items in the interval, we can do it efficiently cache obliviously, because we really want log squared n divided by b. And we say that via constant number of interleaved scans. Scans, we know, as long as there's a constant number of them, and your cache has at least a constant size, number of blocks, then interleaved scans are always going to be efficient. You always get to divide by b. Okay, but the focus will be on making sure the interval is small. The rearrangement will actually be very simple, so not too hard to do. So this will give us log squared n over b amortized memory transfers. So that was the black box we needed to get cache oblivious B trees. Remember, we got rid of the square and the log by using a level of indirection. That removed one of the logs. So we got log n over b. So we were dominated by log-based b of n, which is what we had for the search over here. So this is the step we need. And this is a general tool. It's used in a bunch of different cache oblivious data structures. It's sort of one of the first cache oblivious data structure tools. It's pretty handy. It's actually much older than cache oblivious or external memory models. This results removing the last line and this part, which makes it efficient in this model. Just thinking about moving around intervals in a file goes back to Itai, Konheim, and Rota in 1981. So it's pretty old. And then it was brought to the cache oblivious world in 2000, right when this model was getting started. Okay, so that's the goal. Now let me tell you how this is going to work. So a rough idea is very simple. You have your array, and when you insert an item, what we want to do is find an interval containing that item of some reasonable size that's not too full and not too sparse. If we can find, so like right here when we're inserting 9, it looks really bad right around there. And so there's like too many elements packed right around that element, but that feels bad to us. So we grow an interval around it until we've got enough gaps, and then we just evenly redistribute the items in that interval. So that's basically what we're going to do. We just have to find the right size interval to rearrange items in. But then when we do the rearrangement, it's always going to be evenly redistributing within the interval. So that strategy is simple. And to think about intervals in a nice controlled way, we're going to build a binary tree, our good friend. So let me just draw this binary tree. Yeah. Now, I need to do something a little bit special at the leaves. I'm going to cluster together log n items. So down here is the array, and all of this stuff up here is conceptual. We don't really build it. In my lecture notes, I can just do copy and paste, and this is a lot easier. So we have these chunks of size theta log n at the bottom. Don't really care what the constant is. 1's probably fine. Okay, so this is the array down here, and we're splitting every log n items, or log n cells in the array. And then we say, okay, well, conceptually build a binary search tree here, and then this node represents this interval. And this node represents this interval. Okay, every node just represents the interval of all its descendant leaves. We've seen this trick over and over again. But we're not going to build any data structure or have some augmentation for each of these nodes. It's just, this is how we're going to build the intervals. We're going to start at the leaf. Let's say we want to insert an item in here. So we insert it here. If there's not room for it, we're going to walk up the tree. Say, okay, if this interval is too dense, I'll look at this node and its corresponding interval here to here. If that's still too dense, I'll walk up to the parent and so look at this interval from here to here. And so on until I find, in the end, at most, I redistribute the entire array. And when I do that, I'll just evenly redistribute. Okay, let me write down the algorithm for update. So for insert or delete, same algorithm. You update the leaf log n chunk. You can do that just by rewriting the entire chunk. We can always, we're trying to get a log squared n bound, so we can afford to rewrite an interval size log n. So that's for free. So whatever leaf contains the element you want to insert or delete. And then we're going to walk up the tree until we find a suitable interval. And we're going to call that node, or that interval, within threshold. Okay, so let me define within threshold. We're going to look at the density of a node or an interval. And that's just going to be the ratio of the number of elements that are actually down there versus the amount of slots in the array that are down there. So just how much is occupied. So look at that ratio. If it's 100%, then there are no blank cells down there. If it's 0%, then everybody is blank. So we don't want either of those extremes. We want something in between. And we're going to do that by specifying thresholds on this density and try to keep the density within those thresholds. So let me define those thresholds. Okay, the fun part is that the density thresholds that you maintain depend on which level you are. Not like experience points, but in which height of the tree you are. So down here, we don't really care how well distributed the leaves are. I mean, that can't be 0% because then that would be a really big gap. But it could be, say, between 50% and 100%. It could be totally full. And then once it's overflowing, then we've got to go up. And the higher we go, the stricter we get. Hopefully Yes, strictest at the top of the tree. So, in general, if we have a node of depth d, then we want the density to be at least 1/2 minus 1/4 d over h. And we want the density to be at most 3/4 plus 1/4 d over h. So h here is the height of this tree, which is going to be something like log n minus log log n, but it doesn't really matter. Just this is depth 0, depth 1, depth h. And so we just are linearly interpolating between, let's see, this is always between 1/4 and 1/2. Right, 1/2 when this is 0, 1/4 when this is h. So you get 1/2 minus 1/4. And this one is always in the range 3/4 to 1. It's 3/4 when this is 0 and 1 when this is h. So at the bottom, I was a little bit off. At the bottom, the leaf level, when these are both h, it's going to be, the density has to be at least 1/4 and at most 100%. And then at the root, it's going to have to be between 1/2 and 3/4. So it's a narrower range. And the higher you go up, the more narrow the range on the density gets. And we do it just sort of in the obvious linear interpolation way. The not so obvious thing is that this is the right way to do it. There's a lot of choices for how to set these density thresholds, but we have to basically maintain constant density everywhere because we're trying to maintain gaps of constant size. So we don't have a lot of flexibility, but it turns out this flexibility between two constants, like 1/4 and 1/2, is enough to give us the performance we need. So let's see why. Let me finish this algorithm. We walk up the tree until reaching a node within threshold. Density is this. Density threshold is this. And now we know what within threshold means. And then we evenly rebalance or redistribute all the descendant elements in that interval that is within threshold. So what you need to check is that you can do this with a constant number of scans. It's not that hard. Just read the elements in order, write them out to a temporary array, and then write them back. Or if you're fancy, you can do it in place. But you can just do it by a constant number of scans through the array. Cool. Just compute what is the, what should be the average gap between the elements. Leave that many gaps. Okay, so algorithm is pretty simple. Once you say, okay, I'm going to grow intervals, then maybe you think, okay, I guess I'll grow intervals according to a binary tree. It's a little bit more controlled. Probably don't have to do it this way. You could just grow them by a factor of 2, just around your point, but it's easier to analyze in the setting of a binary tree. And then once you're doing that, the tricky part is to set the density thresholds, but you fool around, and this seems to be the best way to do it. Now the question is, why does this work? How do we prove log squared amortized interval size when we follow these density thresholds? Notice that we're not keeping intervals within density at all times. The whole problem is that things are not within threshold right at the start, and we have to walk up the tree quite a ways potentially. Claim is only about log n levels up the tree to find something that's within density, and then we can redistribute, and then we fix everything below us. All right, well, let's get to that. This is really the direction we want, that thresholds are getting tighter and tighter, more constrained as we go up, because it means if we walk up a lot, we essentially can pay for it because we bring that interval even farther within threshold. So we have some node, which is within threshold. So we bring it into the density thresholds of here. If we look at the children of that node, their density thresholds are smaller, are more relaxed. So if we bring this node into threshold by rewriting all the leaves down here, these nodes will not only be within threshold, they'll be far within threshold. If you look at their ratios, their densities, the number of elements in there, divided by the array slots, it's going to be exactly the same. The density is equal because we're uniformly distributing the items here. And there's some rounding errors, but other than rounding, and that's actually why we have these leaves of size theta log n, so the rounding doesn't bite us. If we're evenly redistributing, so the density is equal everywhere, left child will have the same density as the parent. But if you look at the density thresholds of the child, they will be more relaxed compared to the parent. So if the parent is within threshold, the child will be far within threshold by at least a d over h additive amount. Sorry, 1 over h, because their depths differ by 1. If this is d, this will be d plus 1. Okay, so when we rebalance a node, we put the children far within threshold, meaning if we look at the absolute difference between the density and either the upper threshold or the lower threshold, that will be I guess at least 1 over 4h. Because we're increasing d by 1, and it's 1 over 4h for each step we take. Okay, so the children are extra happy. We walked up here because before, let's say we walked up this path, so we walked from the right child. We didn't stop here, which means this node was was beyond threshold. Okay, but now we walked up, and now we fixed this entire interval, and now it's far within threshold. So before it was, the density minus the threshold went the wrong way, had the wrong sign. Now we're good, and we're good by at least a 1 over 4h. Now h here was the height of the tree. It's like log n minus log n. All we need is that this is theta log n. Sorry, theta 1 over log n. H is theta log n. And this is a ratio, 1 over log n, of the number of items versus the number of slots. But we know the number of slots we're dealing with is theta log n, and so this is at least one item. So this log n is designed to balance the h here. Okay, cool. Let's go over here. So the idea is if we're far within threshold, we can charge to those items. That's our goal. So what we're interested in, if we just rebalance this node, say x, we want to know when is the next time x could be rebalanced. Okay, for x to have to be rebalanced, that means, again, one of its children would have to be out of threshold, and then we insert or delete within that child, and then that propagates up to x. But right now, the children are far within threshold. So the question is, how long would it take for them to get out of threshold again? Well, you'd have to change the density by at least 1 over an additive 1 over log n. If you multiply by the size, it's the size of the interval divided by log n. You've got to have at least that many insertions or deletions. So before this node rebalances again, one of its children must get out of balance. And so you must have done at least size of the interval divided by theta log n updates for one of the children to become out of balance again. Boom. Okay? So when this rebalance happens again, we're going to charge to those updates, which is good because the time it takes us to do the rebalance is the size of the interval. So we need to charge to each of these items log n times. Okay, so charge the rebalance cost, which is theta size of the interval, to these updates. And what we know is that the updates are within the interval. Okay, cool. So this looks like a log n bound, which is not right. It should be a log squared n bound. The idea is when we insert into one of these leaves, we're simultaneously making this node worse, and this node worse, and this node worse. Right? Whenever we insert a node, it belongs to log n intervals that we care about. So in fact, not only are we losing this log n because there aren't quite enough items to charge to, log n factor less, we're also charging to each item another factor of log n times because it lives in all these different intervals. Yeah. Each update gets charged at most h, which is order log n times. As we looked at what happens for node x, but we have to apply this argument simultaneously for all nodes x. Fortunately, this node versus this node, they don't share any descendants, and so there's no multiple charging. But node x and its parent and its grandparent, all its ancestors, they're all talking about the same nodes, and so they will multiple charge, but only by a factor of log n. That's something we've seen a few times, charging log n times for every node in the tree, like range trees having n log n space in 2 dimensions. Same deal. Okay, so we've got size of the interval divided by log n guys to charge to, which we multiply charge log n times, so we get a log squared amortized bound. So this log n is hard to avoid because we have a binary tree. That's pretty natural. This log n essentially comes from this h. The fact that we can only go from one constant factor to another, and we've got log n different steps to make, we have to do 1 over log n increment every step. That's the best we could afford. That's why these are evenly spaced out in this linear way. But if we had a little more space, we could do better. So that's going to lead us to this list labeling problem. But first, are there any questions about order file maintenance? At this point, we are done. Yeah?
Can you explain again how is it that you get from the size of the interval over log n and, that each...
This amortization.
Yeah, how do you get to the amortized
Yeah, so let me explain it again. So when we do a rebalance of an interval, the cost is the size of the interval, right? We're trying to analyze what is the size of the interval, prove that it's log squared n. So we have this cost of size of interval. We're charging it to the items which just got inserted or deleted into that interval. Before this node rebalances again, but in general we're interested in the jump. We can afford to rebalance every node at the beginning. And then whenever a node rebalances, before it rebalances, it had to be one of its children had to be out of whack. For one of its children to be out of whack, there had to have been an insertion of at least the size of the interval divided by log n, because log n was h. There's a slight discrepancy here. We're talking about the size of the parent interval versus the size of the child interval, but that's just a factor of 2. Okay, so that's incorporated by this theta. So you could have a little theta here too, if you like. Okay, so for the child to be out of whack, we had to have done updates of size of interval divided by log n. So we charge this cost to them. And so we have to charge log n to each of those items, each of those updates. And then there's a second problem, which is everybody gets charged by all of its ancestors, and it has log n ancestors. So in all, each update gets charged at most log squared n times. So you get amortized log squared per update. Other questions? Cool. So that's ordered files. Now we have B trees. We could handle this log squared n. That was okay for B trees using a layer of indirection. But it's natural to wonder whether you can do better. In general, the conjecture is that for ordered files, you cannot do better. If this is your problem setup, if you can only have constant size gaps, you need a linear size array, you need log squared n interval updates. But no one's proved that lower bound. So that's one open question. Another fun fact is we did amortized, but it's actually possible to do worst case. It's complicated. Willard did it in 1992. But let's talk about relaxing the problem. So if instead of saying, well, the array has to be linear size, what if we let it to be bigger? And then you can do better. And this is a problem called list labeling. So I'm going to rephrase it, but it's essentially the same as ordered file maintenance. It's a little bit less restriction. Okay. So it's a dynamic linked list problem like we've seen before. And each node at all times stores a label such that labels are always monotone down the list. Okay, so think of it this way. We have a linked list. And all we're interested in is maintaining this linked list. So we want to be able to say, okay, delete this item and update these pointers. Or maybe insert a new item over here. And so it's going to be linked like that. And at all times in this cell here, we're storing a number, 3, 7, 12, 14, 42, whatever. Could be any integer, let's say. And we need that the numbers are in increasing order down the linked list. Now, I claim this is basically the same as ordered file problem. Just think of this number as being the index in the array that you store it. So this should be strictly monotone. I guess increasing down the list. Okay, that means none of these numbers are the same, so we can store the items, whatever data is associated with this node, we can store that in the array position 3, in the array position 7, in the array position 12. When we insert, we have to find a new label between 3 and 7. Now we're allowed to change the labels dynamically, that's what makes this possible, which corresponds to moving items in the array. Okay, the only difference is about how this is physically done. With ordered file, you have to physically move items in the array. Here, you just change a number, and that's moving the item. Okay, so where this gets interesting is if you allow the label space, which is the storage space of the array, to become superlinear. With ordered files, it doesn't really make a lot of sense to go superlinear, at least not by more than a couple log factors, because time is always at least space. If you have a giant array, you have to initialize it. And you can't afford to initialize an array of, say, n squared size if you're trying to maintain n items. But in list labeling, you can. I mean, if you say, oh, all these numbers are between 0 and n squared, that's no big deal because you can represent a number up to n squared, which is 2 log n bits. So squaring the space is no big deal for list labeling. It would be a big deal for order file maintenance. So that's why we rephrase it. But they're basically the same problem. Okay, just a little less useful for cache oblivious stuff. So let me tell you what's known about list labeling. In terms of the amount of label space you're given, and how good a running time per update we can get in terms of best known results. So what we just saw is that if you do, we just said linear space, but in fact you can get 1 plus epsilon space. You can say, oh, I only want to waste 1% of my storage space in the array. And if you set the theta at the leaves here to the right value, then you can just waste 1% and still maintain an ordered file. I think this is cool from a file system perspective. But in particular, it gives us what we need. And if you go up to n log n space, it doesn't seem to help you much. Best we know is log squared n. As I mentioned, could be amortized or worst case. Okay. If you bump up the space to n to the 1 plus epsilon, so a little bit superlinear, and anything polynomial, then the best we know is log n. And there's actually a lower bound for this result in a particular model. So it seems pretty clear that, at least for these style of data structures, best you can do in this situation is log n. But hey, log n is better than log squared. And then the other obvious bound is if you have exponential space, you can do constant, essentially. Because with exponential space, you can just keep bisecting the interval between 2 items in constant time until you've inserted n items, and then you can rebuild the whole data structure. So that's sort of the trivial result. If you don't care about how big these labels get, and how big they would get is 2 to the n, then you can do constant time. That's really the only way we know how to do constant. So the interesting new result here that I'm talking about is for polynomial space, we can get log n. And rough idea is you just fix these density intervals. Now, you don't have to make it, there's still going to be a d divided by h here, but your spread can be much bigger. So your densities no longer have to be constants. Now we can afford a density, near the root, we can get a density of like 1 over, actually anywhere, we can afford a density of 1 over n. Because if we have n squared slots and only n items to put in them, then a decent density is 1 over n, in fact. It could also be constant. Constant would be all right. So we've got a big spread there from 1 over n to constant, and so we can afford to take much bigger jumps here of like 1 over n. And so that gets rid of this log n factor, essentially. That was the rough sketch. I have written here that the densities we use are no longer uniformly spaced. They're 1 over alpha to the d. Alpha here is some constant in the interval between 1 and 2. And d is the depth. So now we have exponentially increasing densities, which give you a big gap. No longer lose this log n factor. Okay, so you use exactly the same data structure, these different densities. Now you've got room to fill in a whole bunch more densities when you have, say, n squared space. And so you only get the log n factor because of the number of ancestors of a node, and you lose the other log n factor. Okay. Cool. Now let me tell you about another problem. Building on this. So this is the list order maintenance problem. And this is the problem we saw in lecture 1.